I always loved astrophysics, like from a very young age. I just find space really cool.
It allows you to ask the big questions about the universe, questions that make you go wow and quite awe-inspiring.
How did the universe start? How did it evolve and where it's going to end, especially what the fate of the universe is.
Today we're going to have a public lecture which will be delivered by Brian Schmidt explaining the accelerating universe. So we have already known that the universe is expanding, but I think it took the entire scientific community by surprise when Brian and his collaborators found that it's not just expanding, but it's also accelerating.
Why is the accelerating universe so interesting? It all comes down and back to Einstein. That is, we need to have energy that is part of the fabric of space, and then gravity will make that stuff push against itself rather than attract. The only problem is we need to have about 70% of the universe be this stuff that pushes. We also still need 30% of the universe to attract, and we need to have a little bit of a balance. And the dark matter plus atoms, well, as the universe expands, they become less and less strong over time because their density becomes diluted. On the other hand, dark energy is part of space itself, and so its density doesn't change at all. The universe gets bigger, it's just part of space, it's always there, which means dark energy will, over time, become stronger and stronger compared to dark matter and atoms. So that tells you that the future of the universe is dark energy. Dark energy has already won the battle of domination of the universe. The more the universe expands, the faster dark energy wants to push it apart. So the universe is going to be expanding faster and faster over time, so fast that in the future, stuff that we see in the future will become invisible because the material as it travels through space will be stranded by the expansion of space. That is, imagine a galaxy we can see today. A photon trying to get to us in the future will try to get through space. Space will be created, and it will literally get stranded in the expansion of space. Things we see today will disappear in the future. This does not mean you are going to be expanded with the universe. Our part of the universe is not expanding because attractive gravity won. But when we look out to the distant galaxies beyond us, those parts of the universe will be accelerated away. So the reality is, we don't know what dark energy is, and a theorist can always rewrite the future. Anything is honestly possible, but when it comes down to common sense, unless, for example, the dark energy suddenly disappears, then we are looking forward to a universe that will, at an ever-increasing rate, expand, fade away, leaving myself and Mark permanently unemployed in the future. Thank you very much.
One of the most interesting things in academia is working between the traditional silos. So if you look at what's happening in physics and astronomy, well, when I was a student, we talked a little bit about particle physics, we talked about cosmology, but they didn't really do much. Now the big questions are all about where those things come together, using the tools of math to go through and figure out the questions of how particle physics and cosmology come together. And of course, it's not just physics and astronomy and math where this works. It can also be physics and social science, math and engineering, all sorts of interesting areas where you can essentially find low-hanging fruit to change the world.
I am looking at explosions on the surface of neutron stars. These explosions happen because these types of neutron stars are in orbit around a big companion star, and they essentially rip matter off the surface of these stars. This makes its way to the surface, and gradually it builds up and builds up until the density and temperature is high enough that an explosion will happen. I really like kind of computational modelling and coding and that sort of thing. I'm building a model, a computational model, which tests these equations to see if they're working. And then if we know that these equations are working, we can then move on to actually doing physics with them.
I work in an area of theoretical physics called quantum gravity. The two pillars of modern physics are general relativity, which describes the force of gravity, and quantum mechanics, which is the framework which describes the other fundamental forces of nature. And these two theories paint very different pictures of reality, and so they're difficult to unify. If we were successful in finding a theory of quantum gravity, then this would enable us to gain a deeper understanding into black holes and even the beginning of the universe.
I study a particular type of supernova called a superluminous supernova. They are extremely bright. They're probably some of the brightest explosions known to man. We hope to use them to measure distances to very distant galaxies, and through that expand our knowledge on both the history and the origin of the universe.